Who was the first person really? This may surprise you, but there never was a first person because every person had to have parents, and those parents had to be people too. Same with rabbits. There never was a first rabbit, never was a first crocodile, never a first dragonfly. Every creature ever born belonged to the same species as its parents, with perhaps a very small number of exceptions, which I shall ignore here. So that must mean that every creature ever born belonged to the same species as its grandparents, and its great-grandparents, and its great-great-grandparents, and so on, forever. Forever? Well, no, it's not as simple as that. This is going to need a bit of explaining, and I'll begin with a thought experiment. A thought experiment is an experiment in your imagination. What we are going to imagine is not literally possible because it takes us way, way back in time, long before we were born. But imagining it teaches us something important. So, here is our thought experiment. All you have to do is imagine yourself following these instructions. Find a picture of yourself. Now take a picture of your father and place it on top. Then find a picture of his father, your grandfather. Then place on top of that a picture of your grandfather's father, your great-grandfather. You may not have ever met any of your great-grandfathers. I never met any of mine, but I know that one was a country schoolmaster, one a country doctor, one a forester in British India, and one a lawyer, greedy for cream, who died rock climbing in old age. Still, even if you don't know what your father's father's father looked like, you can imagine him as a sort of shadowy figure, perhaps a fading brown photograph in a leather frame. Now do the same thing with his father, your great-great-grandfather. And just carry on, piling the pictures on top of each other, going back through more and more and more great-great-greats. You can go on doing this even before photography was invented. This is a thought experiment, after all. How many greats do we need for our thought experiment? Oh, a mere 185 million or so will do nicely. Mere? It isn't easy to imagine a pile of 185 million pictures. How high would it be? Well, if each picture was printed as a normal picture postcard, 185 million pictures would form a tower about 16,000 feet high. That's more than 40 New York skyscrapers standing on top of each other. Too tall to climb, even if it didn't fall over, which it would. So let's tip it safely on its side and pack the pictures along the length of a single bookshelf. How long is the bookshelf? About 3 miles. The near end of the bookshelf has the picture of you. The far end has a picture of your 185 million great-grandfather. What did he look like? An old man with wispy hair and white side whiskers? A caveman in a leopard skin? Forget any such thought. We don't know exactly what he looked like, but fossils give us a pretty good idea. Your 185 million great-grandfather looked something like this. Yes, that's right. Your 185 million great-grandfather was a fish. So was your 185 million greats grandmother, who is just as well, or they couldn't have mated with each other and you wouldn't be here. Let's now walk along our 3-mile bookshelf, pulling pictures off it one by one to have a look at them. Every picture shows a creature belonging to the same species as the picture on either side of it. Every one looks just like its neighbors in the line, or at least as much alike as any man looks like his father and his son. Yet if you walk steadily from one end of the bookshelf to the other, you'll see a human at one end and a fish at the other, and lots of other interesting great-great-grandparents in between, which, as we shall soon see, include some animals that look like apes, others that look like monkeys, others that look like shrews, and so on. Each one is like its neighbors in the line, yet if you pick any two pictures far apart in the line, they are very different. And if you follow the line from humans back far enough, you come to a fish. How can this be? Actually, it isn't all that difficult to understand. We are quite used to gradual changes that, step by tiny step, one after the other, make up a big change. You were once a baby. Now you are not. When you are a lot older, you'll look quite different again. Yet every day of your life, when you wake up, you are the same person as when you went to bed the previous night. A baby changes into a toddler, then into a child, then into an adolescent, then a young adult, then a middle-aged adult, then an old person. And the change happens so gradually that there never is a day when you can say, this person has suddenly stopped being a baby and become a toddler. And later on, there never comes a day when you can say, this person has stopped being a child and become an adolescent. There's never a day when you can say, yesterday, this man was middle-aged. Today, he is old. That helps us to understand our thought experiment, which takes us back through 185 million generations of parents and grandparents and great-grandparents until we come face to face with a fish. And, turning round to go forwards in time, it's what happened when your fish ancestor had a fishy child, who had a fishy child, who had a child, who 185 million gradually less fishy generations later turned out to be you. So it was all very gradual, so gradual that you wouldn't notice any change as you walked back 1,000 years or even 10,000 years, which would bring you to somewhere around your 400 greats-grandfather. Or rather, you would notice lots of little changes all the way along because nobody looks exactly like their father. But you wouldn't notice any general trend. 10,000 years back from modern humans is not long enough to show a trend. The portrait of your ancestor of 10,000 years ago would be no different from modern people if we set aside superficial differences in dress and hair and whisker style. He would be no more different from us than modern people are different from other modern people. How about 100,000 years, where we might find your 4,000th great-grandfather? Well now, maybe there would be a just noticeable change. Perhaps a slight thickening of the skull, especially under the eyebrows, but it would still only be slight. Now let's push a bit further back in time. If you walked the first million years along the shelf, the picture of your 50,000th great-grandfather would be different enough to count as a different species, the one we call Homo erectus. We today, as you know, are Homo sapiens. Homo erectus and Homo sapiens probably wouldn't have been able to mate with each other, or even if they could, the baby would probably not have been able to have babies of its own, in the same way that a mule, which has a donkey father and a horse mother, is almost always unable to have offspring. We'll see why in the next chapter. Once again, though, everything is gradual. You are Homo sapiens, and your 50,000th great-grandfather was Homo erectus. But there never was a Homo erectus who suddenly gave birth to a Homo sapiens baby. So, the question of who was the first person and when they lived doesn't have a precise answer. It's kind of fuzzy, like the answer to the question, when did you stop being a baby and become a toddler? At some point, probably less than 1,000,000 years ago, but more than 100,000 years ago, our ancestors were sufficiently different from us that a modern person wouldn't have been able to breed with them even if they had met. Whether we should call Homo erectus a person, a human, is a different question. That's a question about how you choose to use words, what's called a semantic question. Some people might want to call a zebra a stripy horse, but others might like to keep the word horse for the species that we ride. That's another semantic question. You might prefer to keep the words person, man, and woman for Homo sapiens. That's up to you. Nobody, however, would want to call your fishy 185 million great-grandfather a man. That would be just silly, even though there is a continuous chain linking him to you, every link in the chain being a member of exactly the same species as its neighbors in the chain. Turned to stone. Now, how do we know what our distant ancestors look like, and how do we know when they lived? Mostly from fossils. All the pictures of our ancestors in this chapter are reconstructions based on fossils, but colored by comparing them with modern animals. Fossils are made of stone. They are stones that have picked up the shapes of dead animals or plants. The great majority of animals die with no hope of turning into a fossil. The trick, if you want to be a fossil, is to get yourself buried in the right kind of mud or silt, the kind that might eventually harden to form sedimentary rock. What does that mean? Rocks are of 3 kinds: igneous, sedimentary, and metamorphic. I shall ignore metamorphic rocks as they were originally one of the other 2 kinds, igneous or sedimentary, and have been changed by pressure and or heat. Igneous rocks, from the Latin for fire, ignis, were once molten, like the hot lava that comes out of erupting volcanoes now, and solidified into hard rock when they cooled. Hard rocks of any kind get worn down, eroded by wind or water to make smaller rocks, pebbles, sand, and dust. Sand or dust gets suspended in water and can then settle in layers of sediment or mud at the bottom of a sea, lake, or river. Over a very long time, sediments can harden to make layers or strata of sedimentary rock. Although all strata start off flat and horizontal, they have often got tilted, upended, or warped by the time we see them millions of years later. For how this happens, see Chapter 10 on earthquakes. Now suppose a dead animal happens to get washed into the mud, in an estuary perhaps. If the mud later hardens to become sedimentary rock, the animal's body may rot away, leaving in the hardening rock a hollow imprint of its form, which we eventually find. That is one kind of fossil, a kind of negative picture of the animal. Or the hollow imprint may act as a mold into which new sediments fall, later hardening to form a positive replica of the outside of the animal's body. That's a second kind of fossil. And there's a third kind of fossil in which the atoms and molecules of the animal's body are, one by one, replaced by atoms and molecules of minerals from the water, which later crystallize to form rock. This is the best kind of fossil because, with luck, Tiny details of the animal's insides are permanently reproduced right through the middle of the fossil. Fossils can even be dated. We can tell how old they are mostly by measuring radioactive isotopes in the rocks. We'll learn what isotopes are and atoms in Chapter 4. Briefly, a radioactive isotope is a kind of atom which decays into a different kind of atom. For example, one called uranium-238 turns into one called lead-206. Because we know how long this takes to happen, we can think of the isotope as a radioactive clock. Radioactive clocks are rather like the water clocks and candle clocks that people used in the days before pendulum clocks were invented. A tank of water with a hole in the bottom will drain at a measurable rate. If the tank was filled at dawn, you can tell how much of the day has passed by measuring the present level of water. Same with the candle clock. The candle burns at a fixed rate, so you can tell how long it has been burning by measuring how much candle is left. In the case of a uranium-238 clock, we know that it takes 4.5 billion years for half the uranium-238 to decay to lead-206. This is called the half-life of uranium-238. So, by measuring how much lead-206 there is in a rock, compared with the amount of uranium-238, you can calculate how long it is since there was no lead-206 and only uranium-238. How long, in other words, since the clock was zeroed. And when is the clock zeroed? Well, it only happens with igneous rocks, whose clocks are all zeroed at the moment when the molten rock hardens to become solid. It doesn't work with sedimentary rock, which has no such zero moment. And this is a pity because fossils are found only in sedimentary rocks. So we have to find igneous rocks close by sedimentary layers and use them as our clocks. For example, if a fossil is in a sediment with 120 million year old igneous rock above it and 130 million year old igneous rock below it, you know the fossil dates from somewhere between 120 million and 130 million years ago. That's how all the dates I mention in this chapter are arrived. They are all approximate dates, not to be taken as too precise. Uranium-238 is not the only radioactive isotope we can use as a clock. There are plenty of others with a wonderfully wide spread of half-lives. For example, carbon-14 has a half-life of only 5,730 years, which makes it useful for archaeologists looking at human history. It is a beautiful fact that many of the different radioactive clocks have overlapping time scales, so we can use them to check up on each other, and they always agree. The carbon-14 clock works in a different way from the others. It doesn't involve igneous rocks, but uses the remains of living bodies themselves. For example, old wood. It is one of the fastest of our radioactive clocks, but 5,730 years is still much longer than a human lifetime. So you might ask how we know it is the half-life of carbon-14, let alone how we know that 4.5 billion years is the half-life of uranium-238. The answer is easy. We don't have to wait for half of the atoms to decay. We can measure the rate of decay of only a tiny fraction of the atoms and work out the half-life, quarter-life, hundredth life, etc. from that. A ride back in time. Let's do another thought experiment. Take a few companions and get in a time machine. Fire up the engine and zoom back 10,000 years. Open the door and have a look at the people you meet. If you happen to land in what is now Iraq, they'll be in the process of inventing agriculture. In most other places, they'll be hunter-gatherers moving from place to place, hunting wild animals and gathering wild berries, nuts, and roots. You won't be able to understand what they say, and they will be wearing very different clothes, if any. Nevertheless, If you dress them in modern clothes and give them modern haircuts, they will be indistinguishable from modern people, or no more different from some modern people than people are different from one another today. And they will be fully capable of breeding with any of the modern people on board your time machine. Now, take one volunteer from among them, perhaps your 400 great-grandfather, because this is approximately the time when he might have lived, and set off again in your time machine back another 10,000 years to 20,000 years ago, where you have a chance to meet your 800 great-grandparents. This time the people you see will all be hunter-gatherers, but once again, their bodies will be those of fully modern humans, and once again, they will be perfectly capable of interbreeding with modern people and producing fertile offspring. Take one of them with you in the time machine and set off another 10,000 years into the past. Keep on doing this, hopping back in steps of 10,000 years, at each stop, picking up a new passenger and taking him or her back to the past. The point is that eventually, after a lot of 10,000-year hops, perhaps when you've gone, let's resume our journey into the past and look at some of the stations on the way back to that beautiful fish. Suppose we have just arrived in our time machine at the station labeled 6 million years ago. What shall we find there? So long as we make a point of being in Africa, we'll find our 250,000 great-grandparents, give or take some generations. They'll be apes, and they might look a bit like chimpanzees, but they won't be chimpanzees. Instead, they'll be the ancestors that we share with chimpanzees. They'll be too different from us to mate with us, and too different from chimpanzees to mate with chimpanzees. But they will be able to mate with the passengers we took on board at station 5,990,000 years ago. And probably those from station 5,900,000 years ago too. But probably not those who joined us at station 4 million years ago. Let's now resume our 10,000-year hops all the way back to station 25,000 million years ago. There we shall find your and my 1.5 million great-grandparents at an approximate estimate. They will not be apes, for they will have tails. We would call them monkeys if we met them today, although they are no more closely related to modern monkeys than they are to us. Although very different from us and incapable of breeding with us or with modern monkeys, they will breed happily with the all but identical passengers who joined us at station 24,990,000 years ago. Gradual change all the way. On we go, back and back, 10,000 years at a time, finding no noticeable change at each stop. Let's pause to see who greets us when we reach station 63 million years ago. Here we can shake hands. Pause with our 7 million great-grandparents. They look something like lemurs or bush babies, and they are indeed the ancestors of all modern lemurs and bush babies, as well as the ancestors of all modern monkeys and apes, including us. They are as closely related to modern humans as they are to modern monkeys, and no more closely to modern lemurs or bush babies. They wouldn't be able to mate with any modern animals, but they would probably be able to mate with the passengers we picked up at station 62,990,000 years ago. Let's welcome them aboard the time machine and speed on backwards. At station 105 million years ago, we'll meet our 45 million great-grandfather. He is also the grand ancestor of all the modern mammals except marsupials, now found mostly in Australia, plus a few in America, and monotremes, duck-billed platypuses, and spiny anteaters, now found only in Australia, New Guinea. The picture shows him with his favorite food, an insect, in his mouth. He is equally closely related to all modern mammals, although he may look a bit more like some of them than others. Station 310 million years ago presents us with our 170 million great-grandmother. She is the grand ancestor of all modern mammals, all modern reptiles, snakes, lizards, turtles, crocodiles, and all dinosaurs, including birds, because birds arose from within the dinosaurs. She is equally distantly related to all those modern animals, although she looks more like a lizard. What that means is that lizards have changed less since her time than, say, mammals have. Seasoned time travelers, as we are by now, it isn't far to go until we hit the fish that I mentioned earlier. Let's make one more stop on the way, at station 340 million years ago, where we meet our 175 million great-grandfather. He looks a bit like a newt and is the grand ancestor of all modern amphibians, newts and frogs, as well as of all the other land invertebrates. And so to station 417 million years ago and your 185 million great-grandfather, the fish on page 40. From there we could go on even further back in time, meeting more and more distant great-grandparents, including various kinds of fish with jaws, then fish without jaws. Then our knowledge starts to fade into a kind of mist of uncertainty, for these very ancient times are where we start to run out of fossils. And I'll begin with a thought experiment. A thought experiment is an experiment in your imagination. What we are going to imagine is not literally possible because it takes us way, way back in time, long before we were born. But imagining it teaches us something important. So, here is our thought experiment. All you have to do is imagine yourself following these instructions. Find a picture of yourself. Now take a picture of your father and place it on top. Then find a picture of his father, your grandfather. Then place on top of that a picture of your grandfather's father, your great-grandfather. You may not have ever met any of your great-grandfathers. I never met any of mine, but I know that one was a country schoolmaster, one a country doctor, one a forester in British India, and one a lawyer, greedy for cream, who died rock climbing in old age. Still, even if you don't know what your father's father's father looked like, you can imagine him as a sort of shadowy figure, perhaps a fading brown photograph in a leather frame. Now do the same thing with his father, your great-great-grandfather. And just carry on, piling the pictures on top of each other, going back through more and more and more great-great-greats. You can go on doing this even before photography was invented. This is a thought experiment, after all. It has a picture of your 185 million great-grandfather. What did he look like? An old man with wispy hair and white side whiskers? A caveman in a leopard skin? Forget any such thought. We don't know exactly what he looked like, but fossils give us a pretty good idea. Your 185 million great-grandfather looked something like this. Yes, that's right. Your 185 million great-grandfather was a fish. So was your 185 million great-grandmother, who is just as well, or they couldn't have mated with each other and you wouldn't be here. Let's now walk along our 3-mile bookshelf, pulling pictures off it one by one to have a look at them. Every picture shows a creature belonging to the same species as the picture on either side of it. Every one looks just. Who was the first person really? This may surprise you, but there never was a first person, because every person had to have parents, and those parents had to be people too. Same with rabbits. There never was a first rabbit, never was a first crocodile, never a first dragonfly. Every creature ever born belonged to the same species as its parents, with perhaps a very small number of exceptions, which I shall ignore here. So that must mean that every creature ever born belonged to the same species as its grandparents, and its great-grandparents, and its great-great-grandparents, and so on, forever. Forever? Well, no, it's not as simple as that. This is going to need a bit of explaining. How many greats do we need for our thought experiment? Oh, a mere 185 million or so will do nicely. Mere? It isn't easy to imagine a pile of 185 million pictures. How high would it be? Well, if each picture was printed as a normal picture postcard, 185 million pictures would form a tower about 16,000 feet high. That's more than 40 New York skyscrapers standing on top of each other. Too tall to climb, even if it didn't fall over, which it would. So let's tip it safely on its side and pack the pictures along the length of a single bookshelf. How long is the bookshelf? About 3 miles. The near end of the bookshelf has the picture of you. The far end